Hello everybody, so this is our last episode about working with disks on Linux, and today we are covering the topic RAID, redundant array of independent disks. This is the question, what happens if a disk fails? The advantage of LVM, what we talked in the last episode, is we are quite flexible for the management. We can enlarge and shrink volumes, move blocks. We can also create snapshots and mirroring and everything. And this is an independent concept, so this is a concept of RAID. And the idea there is, what happens if a disk fails immediately? Let's assume we simply unplug disks and we have a head crash or something, and we want to simulate this behavior by forcefully removing one of our disks from our virtual machine. And this is exactly what this cover picture tells us. This is actually what I want to set up right now. This is a typical so-called RAID 5 array. This works with at least 3 disks, so we have to use 3 disks. We can also use 4, 5, 6, 7, 8 disks, but the minimum version is we use 3 disks, and this is what we want to set up. And then we will see what happens if one of them fails. I start by the same setup as last time. So again, I'm inside my virtual machine, and we start by having a look up what is the current status of our disks. As usual, I start with the parted-l command, and see, this is the original setting. I removed all the disks from the last episode, so we have only this system disk, dev SDA, and we have this unused DVD-ROM, so we don't use this one. And the first thing what I will do is I will add 3 more disks, which then is combined into a RAID array. Remember, I used the PowerShell command to add those disks, and then we can format, and we can then partition and convert this into a RAID array. So actually these are the same commands as last time. In this case, I start by creating a new disks of 1 GB each. So start with disk 1. So this is my first disk. I create a second one. This is my second one, and finally disk number 3. So now we have 3 disks, and actually I will attach these disks to my virtual machine with the add command. So I think it's in history, still in history. Yeah, that's the command. So I add the first disk to my machine, I add the second disk to my machine, and I add the third disk to my machine. Actually, in reality, you can also do this while your computer is powered on, as long as you have what's known as hot pluggable disks. So the modern enclosures allows you to actually remove and add the disks while you have power on. And this is more or less a simulation. Now let's go back to our Linux box and see if we can see the disks inside our box. So let's again do this parted-l command, and here what you see, we have these 3 new disks. Of course, again with the error, because it's quite an empty disk, nothing in it yet. So that's the idea. Now we will do the same. We can create a partition and create a label. In theory, we could use the complete disks to add this as part of a RAID array. So this will work, because if this is a partition or the entire disk, both are block devices. I normally prefer to create a partition, because this avoids any errors with the parted command. But this is up to you what you actually want to do. Now let's use the same command as before. So we will use parted with dev sdb, and this typical command mklabel gpd mkpart partition 0-100%. I'll make a little bit faster than last time, because this is actually the same commands as before. bc is the command mklabel gpd mkpart partition and 0-100%. ignore, quit, and the same as the last disk, mk label, gpd, and mk part 0 to 100%. So if this is too quick, then have a look at the other episode. I will do this a little slowly. So the only that I've created a full partition spanning the entire disk for the 3 disks, so that this error goes away. And now we see we have these 3 partitions: div SDB, SDC, SDD, with the 1 at the end. And now what we need to do is we need to combine the 3 block devices into a new device. And actually this is what the RAID is doing. It takes 3 block devices and applies this RAID algorithm. Actually this is a XOR for each block, and then it creates a new device which then can be used for formatting and mounting. So the command is mdadm. This is the command what we need in Linux, mdadm, for managing RAID arrays. And we will create a new one, -- create. And then the name of the new device. So this is the output device what we will use then for mounting, def md0. So normally it starts with md and then a number 0, 1, 2, 3. So this is the newly created, which is then assembled together out of the 3 other block devices. Then we need to define the RAID level. So we have different levels. Remember, we talked about this in our lecture. RAID 1, RAID 4, RAID 5, and so on. RAID 0, different options. Most of the time we use RAID 5. This is the most common option. Level 5, this is a RAID 5 array. Then we have to specify the number of disks, what we need for the array. In our case we have 3 disks. N is 3, so we have 3 disks. And then the block devices. Def SDB1. See, I use the partition, not the entire disk, to assemble the array. This is why we have this 1 at the end. Then the second one is def SDC1, and last one is def SDD1. So these are my 3 partitions for my 3 disks. And yeah, then that's it. Then the RAID array is ready, that's all. That's quite easy. And then the kernel is calculating this XOR algorithm for us, and the output is a new device now called MD0, which can be used the same way as a regular disk. So actually this is the same operation as a regular disk. There's a nice proc type to have a look inside the RAID arrays in the kernel. This is always good to check out what's going on. And it's simply a file. It's called proc mdstat. This is the status of the RAID arrays. Inside is a pseudo proc device. So what you see there, we have MD0. This is what we just created. This is an active RAID 5 consisting of these 3 blocks devices, and this is a little bit more information about the blocks. And the important thing, have a look at the last part here. This UU means all the disks are up and running. So this is now in full redundant state. So redundant state means a RAID 5 array tolerates the failure of a single disk. Then it's run in degraded mode, and we can still use this data, but then when we can, of course, the idea is then to replace the disk, to replace the faulty disk. So now that we have a new device available, this MD0 can be used as a regular device. So that's all. So let's see if you see this with the parted_l command. Is this available there? Yes, it's here. You see this is now our new device, which actually is made up of these 3 other block devices. And of course you can also create a label and a partition out of this. In this case I will do this. So parted def md0. So this is now partition inside the RAID array. Same command again, mk label gpd mk part 0 to 100%, ignore the error and quit. And again do the parted_l, and now we see this error is gone. Now we have this MD0 device. This is the redundant array. Of course, never ever use the other block devices now, because these are now part of the RAID array. You should not touch the other disks right now, because this is part of the RAID array. But you see now we have this array def0 with one partition, and this is a regular partition what we can use and mount on, and that's the same as on the first episode. Now let's format this disk and mount it. That's the same. mkfs, make file system, type is ext4, and now the correct number is def md0, and now we would have to use a 1. The problem is if we have two numbers directly in between, then Linux uses an intermediate character. It uses p1. This is to separate those two numbers from each other. So this is the correct name is md0 partition 1. So this is actually what this name is all about. And oops, failed execute. ext4, sorry, the type is ext4, not ext. Okay, so this is the correct setting. Now we have a file formatted on it, and now I can mount it. Same as before, mount def md0 partition 1. I use the same directory as before, the data file, and now it's up and running. Now we are full redundant with the RAID array. That's it. Let's have a look with the df command, df-h, to see if this is in place. And now we see the mount is mounted on the /data file, and have a look at the size, please. So the size is 2 GB, and the available size is a little bit smaller. This is 1.9 GB. Why 2 GB? Because we had 3 disks of each 1 GB each, which is in total of 3 GB. But the so-called net capacity, this is the usable capacity, is only 2/3 of it, because the third disk is the redundant disk. So this is so-called parity disk. So when we have 3 disks, only 2 of them are used for data, and the rest is used for parity information. If we would have used 4 disks, then the net capacity would be 75%. So this is a 3/4 of the total disk. So the more disks you use, the better net capacity. In our example, with 3 disks, we can use 66%, or 2/3 of the complete capacity. This is why it only shows us 2 GB and not 3 GB. That's the price to pay for redundancy. Now I can work as usual. Go to this directory, create a file on it, hello world to test.txt, same as what we did before, test.txt. So here's our file, get test.txt, and so on. Now we are working. So now the important thing is what happens if a disk fails. In order to simulate the disk failure, I will remove a disk forcefully from our virtual machine. So I do not do anything inside my virtual machine. I quickly go to outside the PowerShell and try to remove it without any further interaction. So I don't inform the operating system that I will now remove the disk, and hopefully this will detect this removal correctly. So this is how we get. Let's remove one of them. Let's remove the first one. This is how I attach I get the name of the first disk, and then I remove it. Where's my remove command? Remove hard disk H1, and now when I press enter, floop, now the disk is gone. So this is a simulation of a disk failure. Simply forcefully remove the disk. Let's go to our Linux machine and see what's happening. ll, everything working, so that my data is still there, as if nothing has happened. So the user can go on working with the device even though one of them fails. So now let's see with the parted command what we actually have, if this thing is really gone. And you see we have the SDC, and SDD is there, and SDB is missing. So this is what I've just removed, the first one. SDB is missing, so we only have 2 disks, and our RAID array is still up and running. It's now running in degraded mode, which means when another disk fails, then the data is gone. But for now it's working. We can have a look at our status of our RAID array. Again, we have a look at the proc md stat. and this is where we can actually see the failure. You see, we have a look at this part at the end. This underscore means, okay, this is not up and running. We have now only 2 disks for our RAID array, which is our 2 gigabyte in size. And this is, of course, the price to pay, that we only have 2 gigabytes. Okay, so now what happens? What should we do? Of course, we have to replace the faulty disk. And this is normally what an admin is doing. Get some red alert, disk failure. And then we should remove the old one and simply plug in another one. And then what happens then afterwards is, when this RAID array sees the new replaced disk, it starts a so-called resync scan, because the idea of RAID 5 is that it calculates an XOR operation from the beginning to the end. And so this really takes a little bit of time, because we really have to do a full scan for all the blocks on the first disk and all the blocks on the second disk, do the XOR and set the return to the new disk. So this can take up to a couple of hours, depending of course on the size of our disks. Because we have only 1 gigabyte, this is quite fast. And what we will see is then, when we are ready, we should see in full redundant mode again. So now let's go to Windows, and first I removed this really physically, this file. Otherwise we could argue that there's still some data on it. So I really delete the file completely first. This one. So this is the file, what was the simulation of the disks. And now I recreate the disks. So I recreate the disks, and with the name of disk 1. Of course the same size, be careful, it has to be the same size, otherwise there's not a match for the array. So now we have created a completely new drive, which is empty, as we saw. And then we add this thing to our system. So we add this disk 3 again to our system. Is this correct? Yeah, looks good. Okay, now it's there. And go back to Linux. And here we are. And let's again, normally I always start with this parted command to see if the disk has been detected correct. So now what we see this SDB. Of course, it's an error because this is a fresh disk. So now we again do the same, create a partition, and then we reintegrate this thing into the RAID array. Okay, so let's do this thing. Parted /dev/sdb. Verify twice if I'm correct. Yes, SDB. Okay, mk label gpt. And I mistyped this thing, sorry. mk label gpt. mkpart, and again the same settings as usual, 100%, ignore the error and quit please. Quit, so sorry. Good, parted. Check if this is recognized. So now we have this new partition, and now the last thing what remains to be done is I have to reintegrate this into existing array. So let's again add this new hard drive. The command is mdrdm. This is always this RAID array command, mdn, then the device is dev md0. This is our RAID array. And then we add the new disk, add dev SDB1. So this is now reintegrates the disks, and this now triggers the rescan process. Unfortunately, because we are only 1 gigabyte disks, this runs quite fast, so we don't see anything specific except for the redundancy mode. So this now integrates this again into the RAID array. No, this is a double dash. Sorry, it's a double dash add, and now it's added to the array. So let's have a look. I suggest that you simply have a look at the proc mdstat after any change, and you see now it's again integrated again in the RAID array. It's now again up and running, and now we are back in full redundant mode. So now we have replaced the disk, and this integration can take a couple of hours depending on the size of the disk, but for only 1 gigabyte it actually works quite fast. And this is what happens if a disk fails. Remember, RAID 5 only tolerates the one faulty disk, and if you have more than one, then the data is really gone. Of course, this normally happens somewhere in Saturday at midnight. So in reality, when we run RAID arrays, it's quite common that we add what's known as a spare disk. So a spare disk is a fourth disk, which then directly integrates as soon as we lose one of the other disks. Then this rescan process starts immediately and then integrates this into the RAID array, because as long as this is not integrated again, then when the second one fails, then the data is gone. This is the main problem. Of course, we only tolerate one faulty disk. Yeah, and that's it. And again, oh sorry, did I verify that the data was still there? Yes, I think I did. And so now let's have a last look at our data. If our files is there, test.txt, so nothing happens, the user is still happy and working with the array. Okay, so this completes my demonstration about Linux disks, starting with basic disks, logic volume manager, and even RAID array. And that's the basic operation for Linux disks. So please try yourself. So you see, you can do this quite easily with virtual machines, and then you can get in touch what Linux provides us directly in the kernel for managing all this with disks. So that's it. Goodbye.